Okay, everyone, we're going to work on the last unit of this chapter, the logical arguments. It's going to be working with perpendiculars and distance between points. And what we know is that the shortest distance between a point and a line is a perpendicular from that point to the line. It's always going to be the shortest distance. Everybody kind of knows the shortest distance between 2 points is a straight line. So when we have a line, the shortest distance between a point and that line is going to be a perpendicular to the line. So by definition, parallel lines don't intersect. Another way to say this is that two lines are parallel if they are equidistant from each other at every point on the line. So as long as they stay the same distance apart, they're going to be parallel, they're never going to intersect. That's another way to kind of define parallel lines. And again, when we talk about the distance between parallel lines, that's going to be the perpendicular distance between one of the lines and any point on the other line. So like if we had our parallel lines here, we're talking the distance from the two lines is going to be the distance from this point to our perpendicular with the other side. Our perpendicular lines form a right angle, so we're going to have to signify that the lines are perpendicular with the right angle thing. And then in a plane, the theorem that we're able actually to use as we kind of do some proofs later on, in a plane, if two lines are equidistant from a third line, then the two lines are parallel to each other. So think of it, if we have this kind of dotted line, and then we have two lines here outside it, as long as these distances are the same all the way through, then our lines are going to be parallel to each other, and they're also parallel to that third line in between them, if that makes sense. Think of the yellow line down the middle of the road. It's parallel to both sides of the street. Okay. Our perpendicular postulate 2.15, is if we're given a line and a point not on the line, then there exists one and only one point through our line through that point that's going to be perpendicular to a given line. So as an example here, we're going to kind of do a couple of grid problems to see, and then we'll go from there. So we have our points. We have a line P, contains 2 points, the point 66, the point 0, -2, and then there's our line through that point. And then we're also told that point P has coordinates of, that didn't come in very well. We have a point here at point -1,5. And what we're looking to do is we're trying to find the distance from that point to the line. So we are actually going to have to figure out what the perpendicular is to our line. So we have to kind of go back to our line stuff. So I know the slope of my line, slope of a line is y2 minus y1 over x2 minus x1. I have my 2 points for my line. I'm going to make these my x2 and y2 points. So now my slope is going to be 6 minus -2 over 6 minus 0. So I end up with 8 over 6 as my slope, which I can simplify to 4 over 3. So the slope of our line is 4 over 3. I don't really care any other points on the line or what the equation is. I have my point, my slope. Because perpendicular lines, remember, their slopes are negative reciprocals. So what I'm trying to do is find my line through this point that is then going to be perpendicular to our other line. So I got to kind of see where it's going to cross. So what I want to do there is I'm going to have, I know right away that I'm going to use the point slope form. Point slope. So my point slope form of a line is y minus y1 equals m times x minus x1. We remember that from the algebra review unit. So I have a point. I have a point for my thing, and I have my slope. My slope is going to be the reciprocal of the negative reciprocal of 4 over 3. So my new slope for my point slope line is going to be -3 over 4. So then I plug in my other points, so I end up with y minus 5 is going to equal negative 3 over 4 times x minus negative 1, so that becomes plus 1. So that's my equation of my line that goes through there. I have to kind of see where it's going to cross, what my perpendicular point is. So I need to come up with another point that'll satisfy my line. I'm kind of looking at the way the line's drawn. It looks like that point there is where the perpendicular is going to be. So I'm going to plug that point in. It's 3, 2. So so x is 3y. Actually, first I'm going to solve this for yeah. So if I do that, so if I plug the 3 in, I end up with 3 plus 4, so that becomes negative 3. Yeah, so that's what I'm going to do. So I'm going to use this point here as a point 3, 2. What I'm going to do is I'm going to plug that point into my equation here. So my y value is 2, so I'm going to have 2 minus 5 is going to equal negative 3 over 4. My x value for that point is 3 plus 1. So when I simplify this through, I get negative 3 over 4 times 4 is going to equal 2 minus 3, which is negative 3. When these multiply together, those cancel, and I'm left with negative 3 over 3. So this is the point that I need for my other formula to find the distance from this point to that point. Now, we've been talking about distance. We're going to remember the distance formula is always the square root of x2 minus x1 squared plus y2 minus y1 squared, and then take the square root of that. So I have my points. I have a point negative 1, 5, and then I have a point 3, 2. So I'm going to plug those into my distance formula, and I come over in this blank space here. So my x values, x2 is 3. Sorry, lost my train of thought there. So it's 3 minus negative 1, and then all that's going to be squared, plus 2 minus 5, all that's going to be squared, square root of all that. 3 minus negative 1 is 4, so it's 4 squared, plus 2 minus 9 is negative 3 all squared. So I end up with 16 plus 9, all in the square root. So again, that comes down to the square root of 25. So my distance there is going to be 5 units. Does that make sense to everyone? All right, hope that makes sense, because that's how you kind of figure out the distance from, we're kind of using everything we've learned in this unit, distance formula. Sorry, not this unit, the last unit with the basics. This is like the distance formula, old algebra where perpendicular lines have negative reciprocals of other lines and all that good stuff. Okay, that was another sheet to kind of go through. Sorry about that. I mistakenly put 2 things in there. Okay, so now here we're going to find the distance between 2 parallel lines. And again, what I'm looking to do is I'm going to just quickly graph the 2 parallel lines so you see what they look like. So that's where they are. Now I need to find the distance between these 2 points, these 2 lines. I also have to find the perpendicular again. So my perpendicular line to either one of these lines is going to have a negative 1/2 slope. Does everybody see that? Opposite reciprocal of 2, my slope for my new line is going to be negative 1/2. I have a couple points. I have a couple of x-axis, I have an x-intercept, looks like. I have a couple of y-intercepts, so I can create my my equation of a line again. I'm using point slope form. There we are. I plug in a point, so I'm going to plug in 0, 6 for my x and y values. So I end up with y minus 6 equals negative 1/2 x minus 0. So if I really want to look at it, I kind of multiply that through, and it will y minus 6 equals negative 1/2 x, and add 6 to both sides to move that. So the equation of my perpendicular line is -1/2 x plus 6. So that's that. Now I want to find a perpendicular point on the other line. So I kind of look and see. So I'm going to end up kind of drawing in this line is what I'm drawing in. Perpendicular wise. Oops, sorry about that. So it kind of looks like I'm going to have a point that x value is going to be 3. So let's plug 3 in and see what I get. Sorry, this is so negative. So if I plug 3 in for x, I get y is going to equal -1/2 times 3 plus 6, -1/2. So 1/2 of that's really going to be ugly. What an ugly problem. Why did I pick this problem? All right, skip that problem. We're not going to cover that. I am so sorry about this. I don't want to kind of don't want to cover that. Sorry about that. So we have talked about the perpendicular lines, finding the perpendicular distance. I showed you how to do that on that example problem. So now we're going to actually go back and to do some review proofs. We have a couple of givens here. We're given AB is perpendicular to BD. So we know right away, perpendicular, we can draw it in, right angle. We also know that angle EFG is complementary to angle CDB. I know looking at it doesn't look complementary. Just remember, we're not looking at scale drawings of our diagrams. We don't have to worry about scale. We're trying to prove that angle EFG is congruent to angle ABC. So we're going to start our proof. We have our statements and our reasons. So obviously I want you to take some time, take some time and kind of try to prove this out. See if you can do the proof yourself. If you can't, no worries. Come back and take a look at the answers. If you can, then you can check your answers and make sure you got everything right. Okay, so we're going to have our statements and our reasons. We're always starting with our given. AB is parallel to BD, is perpendicular to BD. That's your first given. EFG is complementary to CBD. There's your second given. So we've gotten rid of all the givens, got everything out of the way. So now we're kind of looking, if we kind of think of, kind of building on the AB is perpendicular to BD thing, we know that angle ABC plus CBD has to equal 90 degrees because of, that's right. We're told it's right angle first. We want to go right angle because that's what we're told because of the perpendicular lines form right angles. Now we can go to where I was going the next one. We have to state that that means that ABD is a 90-degree angle. Definition of a right angle, because that's what right angles are. Then we're able to say ABC plus CBD equals ABD. Because again, that's the angle addition postulate. We know that two angles together that share a common side can add up to the bigger angle. From there, we're able to say then that the measure of ABC plus the measure of CBD equals 90 degrees. That's just substitution. We've substituted a measure of angle ABD out. We can then say that ABC is complementary to CBD because that's what complementary angles do. They add up to 90 degrees. So again, that's definition of complementary angles. And then from there, we can say that EFG is congruent to ABC because complements of the same angle are congruent. So we were able to prove that ABC was congruent to CBD. We already knew that CBD was congruent to EFG. So therefore, we can say that they are they're congruent to each other. I hope that makes sense. I hope you were able to kind of figure that one out yourself and get through it. because we really need to start getting to the point where we can do these proofs and have a good understanding of how to get from start to finish. Here's one more example. We're told that AC bisects BAD. We're also told that AC bisects BCD. So we kind of have that line in the middle there bisects both of those angles that are vectored at C and A. We're also told that angle 1 is congruent to angle 2. We're trying to prove that angle 3 is congruent to angle 4. So again, we start with our givens. AC bisects BAD is a given. AC bisects BCD, again, that was our given. Angle 1 is congruent to angle 2, our third given. We got all the givens out of the way. Now we kind of have to figure out where are we going from there. So we kind of look at it and say, okay, I know they told us something about bisectors, so how are we going to kind of figure that out so we can kind of come out and say that angle 1 is congruent to angle 3 and angle 2 is congruent to angle 4, because that's what bisectors do. That's the definition of the angle bisector. It cuts a big angle into two smaller angles that are the equal size. So we're able to say that angle 1 is congruent to angle 2, or angle 3, and 2 is congruent to 4. So then from there, we're able to say angle 3 is congruent to angle 4 because of substitution. We just basically substituted out some stuff, and now we're able to say that angle 3 is congruent to angle 4 because we had angle 1 and angle 2 were congruent. So because we had this line here, and then we were able to say that this was congruent to that, and that was congruent to that, we were able to substitute angle 4 in for 2, angle 3 in for 1, and that's how we got to the substitution for the last line. And that is our last line of our proof, because we proved that angle 3 was equal to angle 4, or congruent to angle 4. Again, I hope you kind of understood that, understood the flow. So this is like the last proof you're going to see before we start doing review. We'll start working with review and some stuff Monday, Tuesday, and Thursday of next week, just to try to get to the point where our test is going to be next Friday and the next Monday. So maybe on Monday we'll do that's all we'll do is we'll just do proof after proof after proof in class to kind of reinforce how proofs work. I hope everybody has a good weekend, and I will talk to you all on Monday.